Okay, let's begin our lecture. As usual, please feel free to interrupt me with your questions or comments. And today we will continue our discussion of time evolution in quantum mechanics. Let me recall that the last time, starting from the von Neumann equation, we derived the Schrödinger equation that governs the evolution, time evolution of that governs the time evolution of pure states. Specifically, the Schrödinger equation has this form. Schrödinger equation. I h bar d by dt psi of t h of t times psi of t. Okay, here the operator h hat is a Hamiltonian of the system, that is, operator associated with the total energy of quantum mechanical system. And in general, this operator may depend on time. For example, when we are dealing with non-conservative system or open physical system. And from a mathematical viewpoint, the Schrödinger equation is a differential equation of the first order, or the first order in time derivative. Basically, this means, so first order differential equation. Basically, this means that once we have a state of our system at some reference time t0, then the Schrödinger equation tells us what will be the state of the system at any other time moment c of t. Here abbreviation CE for Schrödinger equation. And solving the Schrödinger equation, we are able to find, to predict all the states our system will get through in the course of its evolution. And the evolution defined by the Schrödinger equation is deterministic. There is no room for ambiguity or probability. It is fully deterministic. It expresses mathematically the so-called principle of causality in physics, particularly in quantum mechanics. And another remarkable property of the Schrödinger equation is its linearity. The Schrödinger equation is a linear homogeneous equation with respect to the unknown ket vector psi of t. And basically this means that the space of the set of all its solutions is actually a linear space, so we can freely combine, make some superpositions of particular solution to produce new solutions. Specifically, let we have some initial state at reference time t0, which is given by superposition of two states, psi1 of t0 plus psi2 of t0 with some coefficients c1 and c2, which are in general complex numbers. Then again, applying the Schrödinger equation, we get the ket vector psi of t, which is given by the superposition psi 1 of t plus c psi 2 of t with the same coefficient c1 and c2. So the time evolution respects superpositions, linear structure in the Hilbert space of states of our quantum mechanical system. And we can rephrase this by saying that, by stating that the time evolution, if we think about time evolution as a transformation of the Hilbert space of states, is determined by some linear transformation. It is given by some linear transformation. So there must exist some linear operator, I will denote it by U, of t and t naught, that takes initial state and any initial state at time t naught to the final state at time t. So this operator U depends on two variables, two parameters, t and t naught. And it follows from the definition that when these two parameters are the same, that when t equals t naught, then the operator U should be unit operator, because if time doesn't change, then the state doesn't change too. So this linear map should be given by identity operator. So we have t naught is equal to 1, So this equation can be thought of as an evolution, time evolution law in the finite form, in the sense that this equation with operator U links the states which are apart by a finite interval of time interval, contrary to the Schrödinger equation, which can be thought of as an evolution law in infinitesimal form, because in the right hand side we have actually the right hand side is given by the difference of two nearby in time states. And since these two equations, the Schrödinger one and this, describes the same physical evolution of the same physical system, we might expect that these operators H and U are somehow related to each other. And it is easy to write down this relation in the special case where the operator H, the Hamiltonian, doesn't depend on time. So let us start with the case where H doesn't depend on time-independent operator. Then it is possible to write a formal expression for the operator U in terms of the Hamiltonian, time-independent Hamiltonian H. It has this form. So it involves the Hamiltonian of the system as well as time moments t and t naught. And it is clear that this operator U defined by this formula satisfies this initial condition, because when t equals t naught, the exponent is 0 and e to 0 is just 1. Right? Now let us check that the corresponding state psi of t does satisfy the Schrödinger equation for this particular operator u. We have I h bar d by dt x on psi of t, and this psi of t is given now by u of t naught acting on psi of t naught, and plugging this expression for the operator u, we get this. Now when the derivative hits the exponential function, we get prefactor, which is given h times minus I over h bar. And this combination I over h bar cancels exactly this factor I times h bar. So we are left with h u t naught psi of t naught. But this product is just our state psi of t. So we end up with h on psi of t. So comparing the beginning and the end of this equation, we see that our state psi of t does really satisfy the Schrödinger equation for this operator u. Do you agree? Should I clarify something in this computation? Okay, now let me bring your attention to these two terms in these two intermediate terms in this sequence of identity. This and this. Since the initial ket vector psi of t naught is arbitrary, supposed to be arbitrary, we can divide by this ket vector both the sides of this equality to get the operator equality, namely I h d by dt u t naught is equal to h times u t naught. And from now on, I will use the partial derivative for the derivative with respect to time, because my operator u depends on two arguments, on two times, t and t naught. So to distinguish which argument I differentiate, I will use partial derivative. So this is a consequence of the Schrödinger equation, and this equation involves no ket vectors. This equation, it is a differential equation for the operator u as a function of t, and of course we can supplement this equation with the initial condition that u t naught for consonant times is equal to unit, and the times consonant, the operator is equal to unit. But on the other hand, suppose we have some operator u that obeys this equation, and we are able to solve this equation. Then I state that the state psi will satisfy the Schrödinger equation. So for any operator U satisfying this equation, the corresponding ket vector psi of t satisfy the Schrödinger equation. It is quite easy to see, just multiplying this equation by psi of t naught, both the size of this equation by psi of t naught, then we get I h bar d by dt u t t naught So this equation is just a consequence of that. And now we see that this psi of t, psi of t doesn't really satisfy the initial Schrödinger equation. So, but this equation and its consequence, they work for arbitrary Hamiltonian H. So I can omit this requirement that the Hamiltonian doesn't depend on the time, because we can derive the Schrödinger equation as a consequence of this equation for the operator U. So this requirement of time independent is only crucial to write an explicit form for the operator U through the exponential function. But at the level of equation, we can drop this requirement that Hamiltonian is time independent, so we can work with arbitrary Hamiltonians. And this operator U, this operator U, defined by this equation, is called the time evolution operator. So U t naught time evolution operator, or another name, propagator. Time evolution operator or propagator. By definition, this time evolution operator takes any state at time t naught to a state at time t. That is its job. Okay, any questions? Yes, please. Yes. 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 You're right. Because it depends on the initial time. Let me stress that the evolution operator depends on the initial time. So we can apply this operator ut naught to some arbitrary state at time t prime. So they should agree to each other. So this the same time point. These are the same time points. Okay, and the main property of this time evolution operator is its unitarity. Let us check that operator U, defined by this equation here, is actually a unitary operator. For this end, let us write the product U dagger T naught times U T naught. If the operator U is unitary, then this product is just units. Yeah? Identity operator. But we don't know this at the moment, so let us differentiate this expression with respect to time. So using the Leibniz rule for the time derivative, we can write this as d dagger by dt times u plus u dagger du by dt. And at this point we can use our equation, the fact that the time derivative of the operator u can be expressed through the Hamiltonian h. So here we have the time derivative of the operator u dagger, but it is not hard to find out what this time derivative is actually, because we can apply the Hermitian conjugation to both sides of this equation, and this yields immediately minus I h bar du by dt dagger equals to u dagger h dagger, but h Hamiltonian is Hermitian operator, so I have this identity. Now substituting the above expressions for the time derivatives of the operator u and u dagger, I can proceed as follows: minus 1 over I h bar u dagger h times u plus 1 over I h bar u dagger h u. And it is clear that these two terms cancel each other to give us 0. So actually this product in brackets doesn't depend on t, so u t naught dagger t naught is equal to, let us put t to t naught is equal to u t naught and with the help of the initial condition for the time evolution operator, we readily conclude that this is 1. So we see that the operator u is unitary operator for all times. Okay, as a consequence of the unitarity, the unitarity of the operator u implies that the time evolution preserves the norms of the states. So the scalar product of psi of t with psi of t can be written as psi of t naught times u dagger t naught u t naught psi of t naught, and since the operator is unitary, this operator in between is equal to I1, and we end up with psi t naught, psi t naught. So if the original initial state psi of t naught is normalized, has unit length, then so is the final state psi of t. Okay. Okay, now consider the evolution. Now consider the evolution from some state psi of t naught, from some state psi of t naught to the final state psi of t through some intermediate state at time t1. So that t1 somewhere in between t naught and t. And we can do this, we can perform this evolution in two steps. First, we can consider the evolution from t naught to t1, and mathematically this is given by this formula. Psi of t1 is equal to u of t1 t naught step 1, and step 2 we go from t1 to t. Then psi of t is equal to u acting on u of t1 acting on psi of t1. Do you agree? Now plugging the expression for psi of t1 from the first equation, we can proceed as follows: u t1 times u u1 t0 psi t0, right? On the other hand, we can consider with evolution as a direct transition from the initial state at t naught to the final state at t, and according to this interpretation, the final state is obtained from the initial state by applying the unitary operator t naught on psi of t naught. Again, since the initial state at time point t naught is an arbitrary get vector, we can divide by it and get the following operator identity. Operator identity are namely u t naught is equal to u t1 times u t1 t naught. And this is a key property of the time evolution operator. It is called the composition property. Composition. Composition property. In particular, if we put t equals t naught Then the left-hand side of this equation turn to unit operator, but on the right-hand side we get this product u t naught t1 times u t1 t naught is equal to 1. It's just consequence of this general composition property. And from this quantity we conclude that the operator u t naught t1 is equal that these operators in product, they are mutually inverse to each other, so we can write the inverse to t1 t naught as u of t naught t1. So transposing the arguments of the evolution operator, we get inverse operator. We are inverting it. And since the operator is unitary, we can also write that this equals to u dagger t 1 t naught. So inversion or Hermitian conjugation swap the arguments of the evolution operator. And all these properties above are obvious for time-independent Hamiltonians, where we have some more or less explicit expression for the operator u, for the propagator, that is so in this setting transposing times, interchanging times, we get additional minus sign in the exponent. So and this inverse operators, operator u, and the same is true for the Hermitian conjugation that change the sign due to this imaginary unit in the exponential. Actually, this formula with the evolution operator can be generalized to the time-dependent Hamiltonian, and can be easily generalized to the time-dependent Hamiltonian, provided that these are Hamiltonians satisfy this equation, commutativity condition. That is, Hamiltonians at different time moments commute to each other. Then it is not hard to guess how to generalize this formula for time-dependent Hamiltonian with this additional condition. Namely, we have t naught is equal to exponential of 1 over h bar integral from t naught to t d t1 h of t1 h of t1. If our Hamiltonian is exponential happens to be time-independent Hamiltonian, this exponential reduce to this. So if h doesn't depend on time, we can take this Hamiltonian out of the integral and write it as this. Which yields immediately the initial formula for the evolution operator of time-independent Hamiltonian. And as usual, we understand this exponential function in the sense of power series. So it is actually given by infinite series of the form 1 plus 1 over IH bar, integral from t to t, d t1 h t1 plus 1 over 2 factorial, 1 over a IH bar squared, dt2 h of t2 times integral from t0 to t dt1 t1 and so on. This commutativity condition for the Hamiltonians at different time moments is very crucial. Otherwise, this formal expression doesn't make sense until we, without further prescription, how to order these non-commuting Hamiltonians in the products. But thanks to the commutativity condition, there is no problem with writing these terms. There is no ambiguity in writing these terms. And there is also a formula for the unitary operator, for the evolution operator, in the most general case, where this commutativity condition for the Hamiltonians is not fulfilled. But this formula looks a bit cumbersome. So let me first write it down, and then I will comment on it. So, in most general case, we can write the time evolution operator as an infinite series from 0 to infinity, 1 over IH bar to the n. And now the sequence of repeated integrals dtn t of n, h of tn, tn t naught, dtn, h of tn minus 1, and so on, so forth, up to t naught, t2, dt1, h of t1, and that's it. And notice the order of upper limits. They are ordered in this manner. So t is greater than tn, tn is greater than tn minus 1, and so on. t2, t1, t0. So as a result, any Hamiltonian in this product depends on later time point than all the Hamiltonian on the right to it. So these Hamiltonians are ordered chronologically. So the times increases from left to right. From left to right. That's why this expression, this whole expression is called the time-ordered exponential, or T exponential for short. T exponential. Some people use the term Dyson expansion. Dyson expansion after Freeman Dyson, who probably first invented this form of their evolution operation. And in writing, this whole theory is denoted by T, capital T, X of 1 over H bar, T naught T, D T1, H of T1. And you should understand this notation as a single hieroglyph, whose definition is given by this infinite series. And finally, let us check that this series does really satisfy the defining equation for their time evolution operator. So to do this, we just differentiate this series with respect to time. It is not hard to do, because we now applying the time derivative to this sum, we see that the time derivative hits the upper limit of the leftmost integral, giving us the integrand h at time t. So upon differentiation, I get the sum from n to infinity. So I have no integral sign. I have just h of t. Oh, let me erase this. So I get h of t times 1 over I h bar to the n minus 1 t 0 t dt n minus 1 h of t n minus 1 t0 t2 dt1 h of t1. So now I can move this operator h of t, move this operator out of sum to get 1 over I h bar h of t, and the remaining sum gives me exactly the definition of the operator u. So the remaining sum after change of dummy index n to n plus 1, I get exactly the above expansion for the operator u. So u of t naught. And this is nothing but the differential equation for the time evolution operator. Time evolution operator. Questions, please? Please. Well, in this particular case of time-independent Hamiltonians, you are probably right. So, time-independent Hamiltonian for stationary Hamiltonians, we just have and of course we can decompose this into the product of two factors. Say U1 and U2. And of course both these operators are unitary. In this case you're right, but in general, for time-dependent Hamiltonian it is not true. I guess it is not true. In general, but in this particular case you're right. More questions? If no more questions, let's take a 5-minute break. Okay, let us continue our lecture. So before the break, we discussed the time evolution operator that governs the evolution of pure states. But at the same time, evolution operator may be used to define the evolution of mixed states as well. Suppose we have some initial state, rho 0, at some initial time moment, t naught. 0 is state, either pure or mixed, is described by some statistical operator, rho naught, and as with any Hermitian operator, we can write its spectral resolution. So we can write it as a linear combination, superposition of the projectors. Here cats n are eigenvectors of the statistical operator rho naught with eigenvalues lambda n. In physical terms, this number lambda n is just the proportion with which n pure state described by ket vector n enters this mixed ensemble. And let us suppose that these proportions lambda n do not change with time, so they are constant. Let us suppose that our numbers are constant. Then the evolution of the whole mixed state rho is due to the evolution of pure subensembles defined by these ket vectors n. But we know how these pure states, pure subensembles evolve in time. For this we have our time evolution operator, so we can write that n of t is given by u of t naught acting on the initial ket n. And the same is true for the corresponding bra vector. For bra, we have n u dagger t naught gives us the bra vector at time t. Now, substituting these bra and ket vectors into the statistical and into the spectral resolution for the statistical operator, we get the operator rho of t, which is given by the sum over n lambda n and t, or with count of the definition, we can rewrite this as T naught, rho naught, U dagger, T naught. And by construction, this operator, statistical operator of T, satisfies the von Neumann equation. Satisfies the von Neumann equation for mixed states. That is, as well as the boundary initial condition that rho of T0 is equal to rho naught. Now, by the way, from this representation for the statistical operator, it is clear that this operator rho of T is Hermitian for all times and satisfies the normalization condition. So a trace is equal to 1, provided that the initial operator rho 0 satisfies this normalization condition. But using this representation, we can easily prove the positive semi-definiteness of the operator rho of T, which I promised you to do at the end of this section. Indeed, let us take some arbitrary state psi and consider the sandwich psi, rho of T, psi. Now, using this representation for the time dependence of rho, we get psi U dagger T naught, rho naught, U T naught, psi. So if I introduce this auxiliary ket vector phi, which is y phi, let me put psi of T, which is just U T naught on psi, I can rewrite this as and this is definitely greater than or equal to 0 because the initial operator rho naught is supposed to be positive semi-definite. Yes. Please. Yeah, sorry. Thank you for your comment. So, doesn't matter. The proof is still correct. Okay. If no more questions, then we are passing on to the next topic of the today's lecture. And this part of the lecture will be devoted to the Heisenberg picture. So the next Heisenberg picture. So Heisenberg picture. Okay. And everything we have learned above about the time evolution in quantum mechanics is usually referred to as a Schrödinger picture. As Schrödinger. Schrödinger picture. In this picture, evolution is described in terms of the ket vector psi, which depend on time, while the operators of physical observables stay unchanged. They doesn't depend on time. Doesn't depend on time. Okay. Except for some special cases where the time dependence enters the very definition of the physical quantity, like non-stationary Hamiltonians for non-conservative mechanical system and something like that. As a result, the operators of the same physical observables look the same for different physical systems. For example, we can use the same operator x as an operator of position for electrons or protons or whatever particle we wish, and the same is true for linear momentum operator or angular momentum operator. They all look the same for different quantum mechanical systems. And remarkably, there is an alternative formulation called the Heisenberg Picture. Where time evolution is transferred from vectors to operators of physical observables. So psi's stay constant while operators of physical observables depend on time. The existence of such an alternative formulation follows from the very definition of the notion of state. Let me recall that originally we defined a state as something that carries full information about expectation values of all physical observables. The ket vectors of states have been introduced later on as convenient theoretical construction. So, because given a state vector at some time t, we can compute this the corresponding expectation value of physical observable A by this formula. Provided that ket psi has no 1. And with the help of evolution operator, we can rewrite this expectation value as follows: r psi u of t. Let me suppose that initial time t naught is just 0. Then the operator is just a function of time t. R a u dagger u of t psi. So psi of t is equal to u of t psi. And let us consider this operator r of t in between of states psi. In general, this operator depends on time through the time dependence of the evolution operator. And And this time-dependent operator, A of t, is called the Heisenberg operator. Heisenberg operator. Heisenberg operator of a physical quantity A. A physical quantity A. So we see from this definition that the Heisenberg operator is related to the original operator A, the original operator of physical quantity A, by a non-stationary unitary transformation performed by the operator U dagger. Let me recall you that under unitary transformation, all ket vectors pass to the U acting on psi, and all physical observables described by Hermitian operator pass to U dagger AU. Sometimes people put additional letters H and S to distinguish between the Heisenberg operators and their Schrödinger counterpart. So H here for Heisenberg and here for Schrödinger, but I will not use this notation because it will be clear from the context which operator is meant. Basically, Heisenberg operator depend on time, so I will put the argument of this operator T. And since the Heisenberg operator just are given by the unit transformation, they satisfy all the same algebraic properties, algebraic relations that hold for the corresponding Schrödinger operators. In particular, the Heisenberg operators of position and momenta satisfy the canonical commutation relations. So for the momenta, we have Pi with Pj is equal to 0, and the same is true for the position operators. Qi of t, Qj of t, and the only not real commutators correspond to P and Q. And now using the explicit expression for the time evolution operator for stationary Hamiltonians, we can write this Heisenberg operator A of t above in a more explicit form. Namely, A of t is actually given by e to the it or h bar h a e to the minus it over h bar h hat. And looking at this expression, we can readily conclude that the Heisenberg operator for the energy of the Hamiltonian coincides with its Schrödinger counterpart. So the Hamiltonian of stationary Hamiltonian, the Heisenberg operator of the stationary Hamiltonian doesn't depend on time, because Hamiltonian definitely, certainly compute with their evolution operator. So this evolution operator doesn't affect the stationary Hamiltonian. So let me recap. In the Heisenberg picture, the state vectors of few states do not evolve in time. The time evolution affects only the operators of physical observables. The expectation values, as well as the eigenvalues of physical observables, the quantities that are measured in experiments, remain the same. They do not depend. They do not depend on the picture. Do not depend on the picture. In other words, the Schrödinger and Heisenberg picture differ only in math, in mathematics, not the physics. It is also instructive to rewrite this evolution law for the operators in the Heisenberg picture in differential form. And to obtain this differential form, we can just differentiate this expression with respect to time. So applying the time derivative, we get that dA of t by dt is equal to, so using the Leibniz rule and differentiating first this exponential, then this exponential, I first get h I e to the I t h bar h a now applying the time derivative to the second exponential, I get minus r of h I h bar and I see that this combination is actually A of t, and this combination is A of t, the Heisenberg operator. So finally, I get that dA by dt is equal to 1 over I of h bar A of t with h. And this equation is known as the Heisenberg equation of motion. Heisenberg equation of motion for operators of physical observables. It is noteworthy that this equation coincides in form with the corresponding Hamiltonian equation for classical observables. So in classical mechanics, we would have for a dA by dt is equal to A also in bracket with h. And this form of similarity between the equation is just another manifestation of the correspondence principle. Between classical and quantum mechanics. this equation also resembles the von Neumann equation for statistical operators. Indeed, for all, we had d rho by dt is equal to 1 There is, however, some important difference between these two equations. Do you see? What is the difference? Right. So, using anti-symmetry of the commutator, of course we can write this in this way, but then we have additional minus sign. And we get additional minus sign. So these two equations are not quite the same because of this minus. Although both the equations, the Heisenberg equation and von Neumann equation, describes the evolution of Hermitian operators A and O, the interpretation of these Hermitian operators interpretations are different. A is operator of physical observers, but rho describes some mixed state. So it is not big surprise that these two operators are satisfy slightly different equations of motion. A distinguishing feature of the Heisenberg operators compared to the Schrödinger ones is their non-universality, Their form depends on the form of a particular Hamiltonian, of a particular quantum mechanical system. Let us consider a couple of examples illustrating this feature. And as a first example, let us take a free particle on line, that is one-dimensional motion. Example 1, free particle. Then the Hamiltonian of a free particle is given by this expression, just kinetic energy. And in the coordinate representation and Schrödinger picture, the momentum of our particle is given by the operator d by dx, and the corresponding position operator is just operator of multiplication by the coordinate x. And both the operators do not depend on time. And let us look at the Heisenberg equation of motion for the operators p and x. So in the Heisenberg picture, the dynamics of the operator p is given by this equation d by dt p of t is given by 1 over IH bar p of t with h, right? But h is a function of p, and p obviously commute with p, so we get 0. So for the momentum operator, we have this equation, and it is easy to integrate it to get P of t is equal to P. There, this P, initial value P, coincide with the corresponding Schrödinger operator. So the Heisenberg and Schrödinger operators for the free particle are the same. It is not so hard for the position operator. Let us compute the time derivative of the position operator according to the Heisenberg equations of motion. We have 1 over bar x t to mi h bar x of t squared. Now, using the canonical commutation relations for x and p, we get from this t is equal to minus p over 2m, where p is actually constant operating, doesn't depend on time. So we can easily integrate this equation to get x of t is given by x of t is given by initial x minus t p over m. So this time the position operator depends on time, but these operators, Heisenberg operators, still satisfy the canonical commutation relation. It is interesting to know that we could obtain these quantities for these equations for the time evolution of the operators p and x, just putting heads on the corresponding classical expressions. And again, this is just a manifestation of the correspondence principle. And as the next example, let us consider a simple harmonic oscillator. Example 2, simple harmonic oscillator. This time, the Hamiltonian is given by this expression, p squared over 2m plus m omega squared over 2 x squared. And again, we can write the corresponding Heisenberg equation of motion for x and p. Actually, the commutator x with h we know because only the kinetic energy contribute to this commutator, and we know that commutator of X with kinetic energy is given by minus pi squared over 2m. Now, commuting the operator P with the potential energy, is not hard to get this expression m omega squared x of t. Notice that the resulting system of differential equations, first two differential equations for the operators x and p, is quite similar to what we have in classical mechanics when considering simple harmonic oscillator. The only difference is that now x and p are operators and not just numbers or functions of t. But from this analogy with the classical mechanics, we can expect that the general solution to this system of coupled equations general solution is given by linear combinations of sine and cosine functions. And this is indeed true. It is not hard to check that these linear combinations of trigonometric functions do satisfy these operator equations. So for x we have x hat cosine omega t minus p over m omega sine omega t, and for the momentum we have p hat cosine omega t plus m omega x hat sine omega t. Sine omega t. Here, x and p are Schrödinger operators of the position and momentum. So x is just x 0. And 0. Okay, now generalizing these two examples, we can now consider the general Hamiltonian of the natural mechanical system. The natural mechanical system. Natural mechanical system is a system with a Hamiltonian of the form. The kinetic energy is given by some quadratic function of momentum with some generalized masses m a. Let our system to have n degrees of freedom plus potential energy as a function of the position operator. Function of position operators. Now, writing down the corresponding Heisenberg equations of motion, we get the x by dt is given again by minus p a of t over ma, and for the momentum pa we get d by dt is equal to gradient of the potential function evaluated at the position operators, that is du by dx a of x1 x n of t. That's it. Now we can substitute this momentum entering the first equation to the second equation, so we can exclude the momentum from this system. We can solve this. The first equation for PA and then substitute them to the second equation. The result of substitution is always is almost obvious. Ma d squared xa dt is equal to minus du by dx x and t. Do you agree? And this last equation can be called the quantum Newton's equation. This is quantum mechanical counterpart of Newton's second law. That is, acceleration is proportional to the force which is given by the gradient of the potential energy. Now, passing to the expectation values, we can write the following equation for the expectation value of the coordinates, values of the coordinates xa. That is ma d by dt xa is given by the expectation value of the force acting upon our system minus dx. And at first glance it might appear that this differential equation for the mean values of coordinates, for expectation values of coordinates, satisfies the classical equations for motion, I mean Newton's equation of motion. This, however, is not quite right, because for this to be true, the right-hand side of this equation for the mean values is just ordinary functions. There is no operators anymore. But the right-hand side should be given by the gradient of potential energy as a function of mean values of the coordinates. So, in order for this interpretation in terms of the Newton's equation of motion was possible, we need the following equality. The mean value, that is the mean force or expectation value of force, is given by du as a function of expectation x expected by dxa. But this equality doesn't hold in general. For example, let us consider the case of cubic potential. Suppose U is given x cubed, right? X cubed. Then our du by dx is just expectation value of x squared, but du of dx expectation value is given by x squared. So in general, x squared minus x mean value of x squared is not zero. Actually, it is a dispersion, quadratic dispersion of x in a particular state. So it is not zero. Maybe zero for some special states, some coherent states, but not in general. So for this, but this equality is always satisfied for the so-called quadratic potential, satisfied for quadratic potential, where U is actually given by quadratic polynomial of coordinates x plus bx plus c. And as particular instances of this, I can mention the harmonic potential, or for a simple harmonic oscillator, or a particle moving in response to constant force, where u of x is given by fx, so that du by dx is just f, constant force. In both the cases, our potential is quadratic, no more than quadratic in x, so these equality is satisfied. So in this case, the mean values of coordinates, evolve according to the classical equations of motion. And this statement about the property of quadratic potential is known as Ehrenfest theorem. Ehrenfest theorem. It's known as Ehrenfest theorem right now. Ehrenfest theorem. Okay, that's all for today. Are there any questions? Oh, you're right again. Thank you. Yeah. If we know the expectation values of all physical observables, not physical observable, but expectation values that are measured in experiments, outcomes of measurements, right? Okay? Yes, in a sense you're right, yes. This was actually my argument why it is possible to pass from Schrödinger picture to Heisenberg picture, because physical observable values are expectation values, not operators of physical observables, of course, not ket vectors in Hilbert space. So, but we can treat the evolution of expectation values either as a result of evolution of operators or evolution of states. So it depends on a particular viewpoint. Yes. More questions? Then let us finish our lecture, and goodbye for today.